Right, gents, so we did Thevenin's theorem last week. This week we're going to do Norton's theorem. So, Norton's theorem says any active network having two terminals A and B can be replaced by a constant current source of current IN and an internal resistance Rn. The value of IN is equal to the current that would flow between the terminals A and B if they were short-circuited, and the value of the resistance Rn is the resistance of the network measured between A and B with the load disconnected and all sources of voltage or current sources replaced by that ideal internal resistance. The resultant Norton's equivalent circuit looks like that below. So we have a current source there that's equal to the short circuit current that would flow at the terminals A and B, and we have Rn in parallel this time for the Norton circuit. That would be the resistance looking back in at the terminals A and B when we replace all sources of voltage or current with their ideal internal resistances. So it's a little bit like the Thevenin's, as a similar thing to Thevenin's, but we're looking at current source and parallel resistance. So let's have a look at an example. Let's have a look at the process involved. Process or procedure to adopt when using Norton theorem is summarised below. To determine the current flowing in a resistance of a branch AB of an active network, we first of all short circuit the branch AB. It must be the whole branch, so if you've got any series resistance in that branch, you've got to take it all out and short. Determine the short circuit Norton current flowing in that branch. So that will give you Rn. So that gives you, IN, the Norton's current. And then you remove all sources of EMF and replace them with our internal resistance. If a current source exists, replace with an open circuit. Determine the resistance looking in at the break between A and B. Determine the current flowing in a resistance from the Norton equivalent circuit. We use the current divider, or alternatively, if you're more comfortable with that, calculate the terminal voltage and use that to find the current. Okay? So, an example circuit. We're going to use Norton's theorem to calculate the current. Now, this is a consistent typo, we'll call that R3. And we're interested in the current flowing in the 30 ohm resistor here, IL. Okay, so we're going to use the Norton's theorem to calculate that current and calculate the power dissipated in this 30 ohm resistor here. So, first off, we take out the 5 and the 30 ohm resistor. We have to take everything in the branch out. Okay, effectively, we've got two terminals here, A and B, and we've put a short circuit. Now, because the 20 ohm resistor is short circuited, we can say that that circuit is equivalent to the one on the right. Because effectively, if this branch is 0 ohms, then no current is going to go through the 20 ohm resistor. It will all go through the 0 ohm branch. Yeah. So we can then, or you can now calculate the Norton current IN, which flows in there. Right, so what's this Norton current then? How do we calculate IN?
24 over 5.
Yeah, that's the VS over R1, 24 over 5 equals 4.8 amps. So that's the short circuit current, and that's the Norton current source that we're going to use in the final circuit. Okay. The next bit is to calculate the Norton's resistance value, which is the resistance looking back in at the terminals A and B, having replaced all sources of voltage and current with our ideal internal resistances. So we've replaced VS with a short. That's its ideal resistance. Or the resistance of an ideal voltage source, I should say. So now how do we calculate that Rn looking back in that terminal? Yeah, Rn are in parallel, so we can use product over sum, R1 times R2 over R1 plus R2, that is 20 times 5 over 25, that's 4 ohms. So we can now put those values, 4.8 amps and 4 ohms, into our Norton's equivalent circuit, which looks like that. So that's 4.8 amps, that's 4 ohms. We then put back in our R4, which is 5 ohms, our RL, 30 ohms, and there are terminals A and B. So that's the what's called the Norton's equivalent circuit, is that bit with the two terminals on, and then we can put a load of load back in here, or any other load, and calculate the consequences of that. This bit here will act just like the original circuit did prior to simplification. So if we use the current divider rule mentioned earlier, IL is Rn over Rn plus RL. We also need to include the 5 ohm resistor in there, because it's in that same branch as the load resistor. Alright, so that's 4 over 4 plus 30 plus 5 4 over 39. That ain't right. Ah, we got to multiply this by n. That's sneaky, that's right on the end there and I didn't see it. Answer now is okay. Now, if you're uncomfortable with the current divider rule or can't remember it, alternative method. We can calculate the total resistance by 4 times 35 over 39, product of a sum rule, 3.59 ohms, it's rounded to 3 significant figures. We can then calculate the voltage at the terminals AB, that is IN, times that RT, which is 4.8 times 3.59 equals 17.23 volts. Show you where that come from. All of that current will travel through that parallel network. Therefore, you can, if you use all of that current with the total resistance, you'll find the terminal voltage. Haven't found that, you can then find IL from VAB over R3 plus RL. That's 17.23 over 35 equals, I've got 492 milliamps, which is different from the other result, only in rounding I would think. We've got 0.49, okay, and then the power in the load is IL squared RL 0.492 squared times 30, which is 7.26 watts. Okay. Everybody reasonably happy with that process?
Let me just, I'll come to your page now.
Yeah, sorry. Everyone happy? Jasmine, yeah? Still a bit. Right, moving on. We're going to have a look at a second example, one that includes two sources. Okay, so using Norton's theorem, calculate the current flowing and the power dissipated in the 8 ohm resistor. Okay, so if we look at this process, the first thing that we need to do is short circuit and form two terminals A and B. We need to calculate the short circuit current flowing through that branch. But we got two sources, so how are we going to deal with that?
You don't want it at all.
Yeah, we do, effectively we do,
Short circuit one and short.
what process did we use when we had two sources? What theorem did we use 2 weeks ago? Superposition. Yeah. So we need a circuit A and a circuit B. What does circuit A look like? Well, we've got a voltage source E1, 10 volts. And a resistor R1, 1.5 ohms. Alright, now if we look at that in isolation, this branch is completely short-circuited, this branch down the middle here, for circuit A, by that, yeah, and therefore we can just do that. Because we're replacing that E2 voltage source, another typo, E2 voltage source with a short circuit anyway, yeah, therefore this branch is short circuited and there's IA. Circuit B, we've got a voltage source E2 and its resistance, and effectively the other branch is a short circuit. So looking at that, we've got E2 there, which is 18 volts, and R2 3 ohms, and the current in this one is going to be going that way. IB. So IA equals 10 over 1.5 and IB (18 over 3) equals 6 amps. Therefore, by superposition, IN is equal to, now these two currents are flowing one way and one the other. That's IA, and IB is going that way. They oppose each other, so the total current is the biggest one, take away the smallest one, and it's in the direction of the biggest one. So IA is the biggest, so it's IA minus IB, 6.67 minus 6, 0.67 amps. So the overall current in this circuit, in green, is 0.67 amps in the direction of IA, which is that way. Yeah. Okay, so that'll be our Norton current, 0.67 amps. The Norton resistance we calculate by short circuiting both E1 and E2, so they've both been replaced with the resistance of an ideal voltage source, and then Rn is the resistance looking back in. So how do I calculate Rn in this case? Product over sum, R1 times R2 1.5 times 3 over 4.5 equals 1 ohm, isn't it? Yep. So Rn is equal to an ohm. So we've got one ohm in there, and In was 0.67, and our original load resistor was 8 ohms. So we've got to put our 8 ohm resistor back in here. And then calculate the load current and power using any method that you prefer. Right, how are we going about it then? How have we calculated?
IL is Rn over Rn plus RL times
IN, RL over Rn plus RL. So you used the current divider rule, yeah? 0.67 times 8. That's Rn, isn't it? Have I done it? Yeah, Rn. Over 1 plus 8.
Gives you 0.074.
Everyone else get that? I got that, yeah. And then, therefore, PL is IL squared RL.
I done into that. What about that? I didn't believe it.
We get the power. Okay. So, in either Thevenins or Nortons, you could get a question where you also have to use superposition because there's more than one source. Yeah. And then that's a circuit A, circuit B, contribution of each added together at the end. Okay. So, in your notes, next thing we got, I already touched on this anyway, but maximum power transfer theorem. I also touched on it with your filters and attenuators, in that you designed with a specific termination resistance so that you match to your source and you match to your load. Maximum power transfer theorem states that the power transferred from a supply source to a load is at its maximum when the resistance of the load is equal to the internal resistance of the source. If you were talking about an AC circuit, you would replace with resistance with impedance. Okay. Hence, for the circuit below, when the resistance, load resistor R, is equal to the internal resistance of the source, little r, then the maximum power will be transferred from source to load. Typical practical applications of maximum power transfer found in stereo amplifier design, seeking to maximise the power delivered to the speakers. Electric vehicle design, seeking to maximise power delivered to the motor. In terms of AC things like amplifier design, the impedance of speakers and the output impedance of amplifiers are specified always at the same frequency, because that's a quantity that varies with frequency, and that's 1000 Hertz. Yeah. So if you don't match your speakers to the output of your amplifier, you're not going to transfer full power. You're not going to get the full power of the amplifier to the speaker. Not going to get as deaf as you want to. No. Right. So one way to find that, what does that look like? Looks like a Thevenin's equivalent circuit, doesn't it?
Sure does.
Yeah. Equally, it could be a Nortons with a parallel resistance as well. Again, maximum power will be transferred when the load resistance or impedance is equal to the source impedance. So, first example you can have a go at all on your own is find the value of a load resistor RL that gives maximum power dissipation and determine the value of this power. You obviously need to determine the internal resistance of everything to the left of RL, so you can use Thevenin's or Norton's theorem to do that. Okay? Have a go. So I'm going to, like I said, go through both methods, both the Thevenin's and Norton's, and show they both give the same answer. I'm going to start with the Thevenin's method. So, as we looked at last week, first thing to do is take out the load resistor and find the open circuit voltage. So, initially, if we can find the current flowing there, then we can find the volt drop across this resistor, which is also the volt drop at the output. Yeah. So I can go by Ohm's law. I is equal to, it's going to be the 25 volts multicoloured today, divided by these two resistors added together, 2.5 plus 15. Yeah, 25 over 17.5 equals 1.429 amps.
No, surely it's 2.5 times by 15.
What's that?
So you put
I. for the RN. Oh, you're doing Thevenins, aren't you?
Yeah, I'm doing Thevenins
right,
at
yeah,
the moment. Yeah, we'll come back to that in a minute. Tom, right?
Apologies.
So we 25 over the two resistors added together give us 4.29 amps. And yes, that is awkward trying to work with this board when that's not writing in the right place. Okay, but so now we can find VOC. It is the current times the resistor R2, 1.429 times 15 equals 21.42 volts. Yep. So that would be our Thevenin's voltage we would use. This calculation is the same whether you use Thevenin's or Nortons, because you're replacing the same source with the same short circuit and you're looking in at the same two terminals, A and B. So here you should have done product over sum.
I think you press it.
R Thevenin's is equal to R Nortons. They're both the same. Yeah. Product over sum. R1 times R2 over R1 plus R2
That's usually the RL, isn't it?
15 times 2.5 over 17.5, 2.14 ohms. Yeah? So that gives us an equivalent circuit where this is 2.14. We're going to make the load equal to 2.14, so we've got maximum power transfer, and the voltage source is 21.42. No, the Thevenin's voltage. The voltage source in the original problem was 25. Yeah? But we've now replaced that with the equivalent circuit. Yeah? So this is like you were doing with the current source earlier. The Thevenin's equivalent circuit is a voltage source and a series resistor.
Yeah.
The Norton's equivalent circuit is a current source and a parallel resistor. Yeah. The resistor will be the same for either of them, but one's a parallel circuit, one's a series circuit, one's got a voltage source, one's got a current source. Okay?
Yeah.
So you can use either for most problems. Yeah. So here, RL IL was equal to V Thevenin's over R Thevenin's plus RL. That's 21.42 over 2 times 2.14 equals 5 amps. There or thereabouts. What we got. And the power PL is I squared RL 5 times 2.14 equals right here somewhere 53.5 watts.
That's 20 watts.
5 squared.
No, that's close, right?
You square your current.
why we're at 72. But we'll come on to that when we do.
Okay, so Nortons, instead of the open circuit voltage, we need to find the short circuit current. So we short circuit the output, that effectively short circuits that resistor, and therefore we don't need to consider it. Yeah. Okay, and therefore IN is equal to 25 over 2.5 equals 10 amps. Yeah. You'll all agree that the Norton resistor is exactly the same as the Thevenin's resistor. Therefore, we've got a Norton's equivalent circuit that looks like this. 10 amps. .14 ohms. There's our two terminals A and B. Okay. And if you looked at doing Thevenin's on this circuit, what's the open circuit voltage? It's 10 amps times 2.14 with the 21.4 volts I got using the Thevenin's method. Yeah. Put our load resistor in, which for maximum power transfer we want to be 2.14 ohms. Yeah. And just simply by the fact that they're both the same, they're going to get half the current each, 5 amps. Yeah. But you can, if you wanted to, you can say IL is equal to IN times RN over RN plus RL. 10 times 2.14 over 2 times 2.14 equals 5 amps. You get exactly the same result. Okay. Exactly the same method as for the Nortons, for the Thevenin's, because you're calculating with that resistor back. You're still only calculating looking back in with the voltage source replaced by its internal resistance, so it's the same calculation. Yeah. Okay. And if you look at the Norton circuit at the end and consider doing Thevenin's on that circuit, yeah, what you're going to replace that with an open circuit because that's a current source. Looking back in at these terminals, you're going to get a Thevenin's resistance of 2.14. So they're the same in either circuit, except one's in series, one's in parallel. Okay. Now, exam-wise, you can pretty much guarantee you're going to get one out of superposition, Thevenin's and Norton's. You may even get a Thevenin's question or a Norton's question that includes a little bit of superpositioning because it's got 2 voltage sources or 2 current sources. So you need to practice these methods so that you understand the method, because I'll also be asking you to explain what you're doing and not just you do the maths. So you'll be expected to understand the process, why you're replacing a voltage source with a short circuit, why you're replacing a current source with open circuit, for instance. Okay. In the other handout that I gave you 2 weeks ago, this learning outcome using network theorems, there are questions involving superposition on page 12, questions involving Thevenin's theorem on page 17, and questions involving Norton on 22, and some maximum power transfer stuff on 27. Okay, all of them have got the answers with them, and if you're getting stuck on one, you can let me know, we can go through it, or I can provide a work solution. Yeah, but you need to get plenty of practice, and there will be typical exam questions towards Christmas as well. Alright, we've got exam on this at Christmas time, after Christmas.
You scroll down to that page, please.
Now, just let me